your three-dimensional body or your three-dimensional structural element, which is a beam, has been modeled as a 1D. That is where it is just like a line. So you may come across, strength of materials and many places where if somebody asks to draw the beam and bending moment diagram, shear force diagram, or you need to draw the stress diagram. So what exactly you will do? You will just draw a line. But where exactly the cross section happen? The cross section is embedded, or you are integrating that cross sectional features, or you are incorporating those cross sectional features to a representative point, and collection of those points are leading to your beam. Now, in a similar way, now we'll look at another class of the structural elements. For example, you have the shells or plates kind of a structures where if you look at the thickness, which is very, very small as compared to its planar dimensions, let's say length and width. So that is where you are again, instead of modeling, instead of analyzing as a three-dimensional plate or a shell, you are representing you are analyzing a mid surface. Usually the reference surface we usually taken as a mid surface, and you can just think of which is exactly mid surface of this. Just think of as you have the book consists of various pages, and the total book is think as a plate, and the mid page you can think of as a surface, and that is where the 2D representation of your actual structure, which is 3D, where we can have the plates or a shell kind of one. So why it is so important over here, and why do we need to look at this dimensionally reducible structures? Because if you look at in finite element analysis, you have number of elements. If I'm able to model any structure using the solid element, then why we are having the beam elements, plate elements, shell elements, or link elements, bar element? So we have different varieties of the elements. Then the very simple answer is the computational cost involved. Let's say if I want to model this, then the kind of a computational cost involved is, you just think of as a beam. If I made it into number of elements, which is also called as subdomains, then how much computational cost involved? Whereas if I made it as a simple line elements, just to think of, let's say I made this beam as a 10 elements. Whereas if I want to model this as a 10, let's say a brick element or a tetrahedral element, how many number of nodes I need to solve, or how many degree of freedom I need to solve, and what kind of a computational cost involved is tremendous. Now that is where we are having varieties of the elements, whether even if you look at especially plates and shells, still people are working on to get a much better representation, especially for a composite material, functionally graded materials, or sandwich kind of a structures, multifunctional composite structures. People are even keep on developing the elements in order to fit the theory which will able to represent your actual 3D structure. Some may be using the very fundamental displacement. Some may be going beyond, let's say somebody looking for a simple linear analysis. Somebody may be looking forward for a geometrically nonlinear or material nonlinear or combined nonlinear, where your physics of the problem or the theory what you are looking forward is different from one to another. So that is where if you look at the finite element literature, you're still, even if you open any kind of a repository of Science Direct or, Springer or any Wiley, you still get a latest publications in terms of the plates and shell theories. So with that small need, or what you call, there is a fundamentally different kinds of elements what we are getting from the geometry. Now I'll be looking at another important aspect is the material. Now we have the very basic one basic type of the materials, let's say metals kind of one, where you have isotropic materials where the material properties are same in all directions, where you just need to provide only Young's modulus and Poisson's ratio as a independent parameters so that you can able to solve the problem. But on the other extreme end, where you have anisotropic materials, where you have 21 constants is required in order to analyze such kind of a material, especially if you look at composite materials which will exhibit anisotropic properties, which are having, there is no symmetry, the properties are different in all directions. So that is where you have a class of anisotropic material. Truly speaking, in nature, all the materials are anisotropic, but to the best possible extent, we'll try to see that how well we can modelize isotropic or an intermediate one, which call it as orthotropic material, where we can find some kind of a symmetric planes, three mutually perpendicular planes of symmetry exist. That is where you have the mechanical, your properties or the material is defined by 9 independent constants. So that is where you have one extreme end, isotropic material, very basic, another extreme end, anisotropic material, and in between you can have orthotropic materials. So this is where you, based on the type of the material what you are modeling, you can have either of them or even a subset of another set of the materials what you can look for. Now I'd like to look at a very basic fundamental quantity, which is another one is the loads. So when you look at a mechanical loads, I'll start with very basic, which is represented by the force newtons, and there is a uniformly distributed load which is spread over the line or along the length dimensions, Newton per meter, and there is one more variety of the load, which is the pressure per unit area or force per unit area what we have. So you can have Newton point load, Newton per meter uniformly distributed load, pressure Newton per meter square, and then you can have self weight kind of a, where it is the Newton per meter cube kind of one. So these are all kind of mechanical loads. In an equivalent way, I'll show you analogous quantities where we can have an equivalent quantities in terms of other fields as well. Now, when it comes to boundary conditions, you have the fixed n, where the degrees of freedom, if you are, or the rotations and displacements are fixed, where you have the vertical displacement and rotation is arrested, and you have only vertical displacement is arrested, or the normal to the surface where it is being supported is arrested. When it comes to boundary condition in literature, you will come across the two varieties of the representation, where we can come across as Dirichlet boundary conditions, where or which is also called as essential boundary conditions. Now, that means you are specifying the displacements. When I am using the displacement, it is equally applicable for rotations also. When I am referring to force, it is also equally refers to moments as well. So another set of the boundary condition, which we call it as natural boundary conditions or Newman boundary conditions, especially mathematics. Whenever you look at papers or books from the mathematics background, they will be using this kind of terminology where Dirichlet boundary conditions or Newman boundary condition. When you look at from the engineering context, where the people uses like a displacement boundary conditions or force boundary conditions in a engineering oriented. So either of the way, I just thought of introducing all of the varieties where people come across, and that is where we can have two varieties of the boundary conditions. Even if you minimize the functional, let's say you minimize the potential energy functional, one set of the, if you first minimization will leads to a set of governing differential equations, and others is a boundary condition. Among those boundary condition, One is the essential, another is natural boundary condition. So people in a different people uses in a different context. So I'm just illustrating in all possible manner so that you are feel like I have already come across this kind of one. Then before I would like to move on, I'd like to introduce three fundamental quantities. If you refer to especially Jane Reddy textbook or his papers, you will find these three terminologies very commonly. What exactly all these? Just to look at, one is the kinematics, second one is constitutive law, and the third is equilibrium equations. So these are the three fundamental quantity equations which relating four fundamental quantities. So if you look at what exactly these four quantities and how these are related to each other. So if you look at, just take an example of, for example, you have a cantilever beam subjected to point load, and you want to find out what is the displacement for corresponding to that load. So for a given force, you need to find out the displacement, or in a reverse way, where you have displacement control formulation, or you are applying the displacement and you want to find out what are the reactions or the forces. So this is the problem in nature. Whereas you have the two virtual quantities, that means imaginary quantities. One is the strain, another is stress. Now these are the virtual quantities, whereas your force and displacements are real in nature. That means I am applying 10 newtons of force. I am getting 3 mm displacement. So you can measure it, you can feel it. Whereas the strain and stress are the intermediate quantities which are relating the forces and displacement. So that is where you have the first fundamental equations in terms of the constitutive law, or the stress strain relationship, which is relating the strains and stresses. There is another set of the quantities or equations which we call it as kinematics, where it is relating the displacement and strain. For example, we will look at very simple case, and it will be more illustrative how these quantities are connected to each other, how these three set of equations will lead to a solution. For example, when it comes to equilibrium equations, which relating the stresses and forces. So what exactly it is going to do is, once you apply the force through this set of three equations which are connecting one to another, forces are connected to stresses, stresses are connected through constitutive law to strain, strains are connected to displacements through the kinematics. So I'd like to illustrate that with a very simple example. Just look at here. You have the cantilever beam, and it is subjected to a point load P. Now I want to find out, corresponding to this load, what is the displacement I can able to get. So that is what the question in our hand. Now it is made up of certain material having the Young's modulus E, Poisson's ratio nu, and the area, cross-sectional area is A, and the length is L. So again, I would like to emphasize the four quadrants. So where you have the geometry, length, and cross-sectional area, the material, Young's modulus, Poisson's ratio, the loads, the force P, and the boundary condition which is fixed at another end. So what we studied, or what we look at in the previous slide, I can bring it over to here. And now I'll like to introduce these fundamental equations. For example, the kinematics, let's say gamma, what I am representing, because I am working in the nonlinear regime, so that this is the usual representation what I use. But very traditionally, let's say epsilon x, which is the change in length by original length. Then stress by strain is Young's modulus. That is nothing but your constitutive law in one dimensionality. And the equilibrium equation is nothing but the stress is equal to force per unit area. Now, the question in our hand is, what is the relation between P and the delta? Now you can start from any equations to anywhere. finally you will end up the relation which is relating delta is equal to PL by AE. So this is the very standard formula what you can get it from the combining these three set of equations, you can able to get this one. So now the point comes, is it really that convenient, or is it possible for all the cases? The answer is no, because we have for example, in case of a 3D, you have 15 set of equations. For example, you have 6 kinematics, 6 constitutive law, and 3 equilibrium equations. That means in total you have 15 equations and 15 unknowns. Mathematically it is fine, but where the problem lies, you have the integral differential equations which need to be solved very rigorously. That is where the problem lies. So there comes the numerical technique in terms of, for example, finite difference method, finite element method, or some other kind of a method where you can able to integrate these set of equations so that for a given load, what is the displacement, or for a given displacement, what is the load kind of one. So fundamentally, these set of quantities you are looking forward, and try to see that how these quantities are related. How do you able to solve this? The analytical method, very simple case I shown, but it is not possible, or it may be very difficult in case of especially nonlinear kind of a situations, or combined nonlinear or multi-physics problems where coupling is taking place. So it will be very difficult to solve analytically such equations where we need to resort to numerical techniques, and that is where the finite element method is one of the versatile and one of the best kind of procedure what we can think of. So with this small background about why and where we can apply the finite element method, I would like to illustrate about the analogous quantities. So maybe first you please pay attention on the table which is on the right hand side, which I already described many quantities over here. When it comes to the structural analysis, usually the unknowns are displacements. Let's say I'm going for a displacement based formulation. Our unknowns are displacements. Then you have the gradients. It is a kind of change in length by original length, which we call it as the strains. That is where we represent the units, unitless quantities, because it is meter by meter, and the usual representation as epsilon. So you try to look at what is the physical quantity, what is the unit, and what is the usual symbol. It is not unique, and it is not this is the only way, but this is also possible representation what we can generally find. The next quantity is the flux, or the force per unit area, which we call it as a stress, which is denoted by sigma Newton per meter square. Then you have these, please don't worry about the terminology, which is actually, in order to relate one analysis with another, it is a little deviated kind of one. But if once you familiarize, once you got a feel of what exactly these quantities, later you will say that these finite element softwares, truly speaking, making money oriented, or I can say I would like to talk about more in a very detailed way how your single program, what you made for structural analysis, which is equally good, or which is equally able to solve your thermal analysis or a flow field problem or some other kind of one. Yeah, you believe or not, is basically internally it is able to solve set of differential equation. Now, what are those equations? Let's say one Laplace equation or a Poisson's equation, and you are trying to solve. But the quantities, what it is going as an input, or what is the unknown quantity, what is the input quantity, will be varying from one field of analysis to another one. So I'm going to talk about now look at here. The first is the displacement. Then you have the strains. Then you have the stresses. Then you have the input, which is in the form of force. Either it may be point force, line force, area based, or the volume like a self weight. and this is where we have the applied force. Then you have the restraints. Restraints means constraints. For example, what you more familiarized, where you can specify the displacements or rotations, and then you are going to find out what are the reaction forces, and then it is made up of certain material where you need to provide these material properties, and that has to follow some material law. For a linear elastic, I am talking about here Hooke's law, where stress is directly proportional to strain. It may not be valid for plastic and other regimes, but a very linear elastic zone, it is applicable. Now, I would like to illustrate, or I would like to have analogous quantities where you have the, let's say I have the code for structural analysis. Can I make use of this for even thermal analysis? The straightforward answer is yes. So that is where I'd like to bring it to your notice. It's not just limiting to again thermal. Even if you go to another field, let's say electrical or some other kind of one, these will be remain same. So what exactly here the unknown? Let's say temperatures, and the temperature gradients are just like a strains, and you have a stress there, you have heat flux, which is again per unit area measures, and you have the source, let's say either heat source, which is a point based, line based, surface or volumetric kind of one, and then you have the specified temperatures where you are specifying over the domain. Then you have the reaction flow, heat flow you can measure, and you can have the material property, just like you have elastic modulus, you have thermal conductivity, and it is following the Fourier's law. So even if whether you observed or not for some time or not, whenever you are working with any finite element analysis, people always say that you have to be consistent with the units. You have to be, you should know what input you are giving. That means what the basic governing equations it is solving. Let's say in your terms it may be displacement, the derivative terms may be strains, then the stress you are calculating, but internally it is trying to look at let's say nodal temperatures or the temperature gradients or heat flux. So this is where the analogous quantities will help you to figure out one set of program. If you make out, that can be utilized in many ways. Then I'll like to introduce one particular case, because we have a very good understanding about now analogous quantities. Maybe I'll illustrate with some heat conduction problem where the temperature is a kind of a case. Now the problem in statement, usually we can have, let's say I want to find out what is the temperature distribution in this bar, or what is the temperature distribution in this wall. Now we can model the physical problem. Let's say this is my wall, some wall, and I want to find out what is the temperature distribution in this when I have given some heat source, and I have I want to see how much it is based on the thermal conductivity, how much it is the distribution is happening from one end to another. This is the physical problem in hand. Now the engineers very smartly, what they will do, they will first take the assumptions, make it more convenient and relevant. Not only convenient, but it is more relevant, so that you will make assumptions saying that it is one dimensional. Why it is one dimensional? Because you are looking forward only the variation of the temperature in one direction, whereas the cross sectionally there is no variation. That is what the meaning. Then the steady state, there is no variation with respect to time, whether you measure today, tomorrow, anytime, it is the kind of one. It is or at least at that particular instance of time, what you are looking is in the steady state, and it is not varying with respect to time. And then there is a thermal conductivity which is constant in all directions, just like you have isotropic material where the Young's modulus is same in all directions. Similarly, your thermal conductivity is constant. Now, based on these assumptions, we are reducing your physical problem to a tractable, or where we can able to minimize your efforts, and at the same time, physics of the problem is not losing. We just need to find out what is the temperature distribution in the bar. Now, that is where you will apply the physical principles. So for example, conservation of energy is applied over here, and we are trying to see how exactly this output, that is the temperature distribution, we can find out. Then comes the mathematical model. Now you have physics in hand. Now you come to the mathematical model that will represent your actual the physics of the problem. Let's say conservation of energy or some other governing differential equations which represent physical principle that need to be represented in the mathematical fashion. So that is where now you take approximations in terms of control volume and other kind of things. I may not get into more details because this is the course which I offer as part of the 6 months course. So most of the slides are extracted from there. So it is a very detailed way some of the slides are, but wherever it is possible, I'll try to curtail, and wherever it is required, I'll try to continue the same. So where, if you look at by applying that principle on the control volume, let's say I have taken very small elemental volume, which is having the dimensions of delta x, delta y, and delta z. So on that, let's say there is a flow coming in, there is a heat generation, whether it is zero or non-zero, let's look at. But this is where you have an input, you have the heat generation is equal to what is coming out as a heat flow out, what is coming out. Now, it's basically like, you have the force balance. Very simple to say that it is a force balance. The sum of the forces in x direction is equal to 0. Same way, you have the analogous quantities in terms of the heat flow per unit area. Then the cross-sectional area, if you multiply, that is the heat flow along that the surface, what it is acting on, let's say dy and dz. Now there is a heat generation. This is per unit volume. Now you multiply with the control volume, then what you can get is the heat generation. That is equal to what is the heat flow out, what is coming out. Because there is something added, there is some phenomena because of thermal conductivity or some other phenomena, what it is passing through this, there is a change in the heat flow. That change, how much it is, that is a secondary quantity, but there is a change. And now that change per unit area is this quantity, and multiplied by the cross section will give you, if you simple arithmetic, if you make out, then the resulting equation is this form. And now we will introduce again, this is one form of the governing equations. You can think of this as the equilibrium equation. Now I talk about 3 set of equations: equilibrium equations, constitutive law, and kinematics. Now if I bring it, the second one, which is the constitutive law, which is relating the stress, the heat flow to strain, which is the gradient of the temperature, where the thermal conductivity, what you can get is K. So now by combining these 2 equations, where I can able to get the governing differential equation, which is nothing but second order differential equation, the thermal conductivity, I bring it out so that it is a kind of a constant, but it is not necessary. You can bring it inside so that it will be function of x. Now, if you look at the governing equations, it is a second order differential equation. Any second order differential equation, which is, if you integrate twice, you will get the solution. Well, that is very basic philosophy what we follow. Now, in order to solve, whenever you integrate one time, you will get integration constant. When you integrate twice, 2 integration constants. In order to solve those 2 integration constants, you need 2 boundary conditions. So when this is where you need to pay attention, one important aspect, which is deviating the governing differential equations, the analytical solution to finite element, where this equation is applicable for entire domain, which ranges from 0 to L. For the entire domain, it is applicable. But when it comes to finite element, this domain will become subdomain, which we calling as element. That is where the beauty of this finite element goes on. Now, when it comes to the boundary condition, for example, at x is equal to 0 or at x is equal to L, which is the extreme ends of the case what we consider, where we specified some temperature or where we specified the flow field, and then we are able to solve using these two boundary condition. I am able to solve this differential equation. This is where we call it as a boundary value problem, where we are specifying the boundary conditions in order to solve this differential equation. And there are ways where we can apply either analytical method, as we discussed, like a traditional integration method, or you can use the finite element method. You can able to solve that. So now we will see what are the differences, where exactly the finite element and the traditional calculus based method will goes on. So when it comes to the starting point, the differential equation and set of boundary conditions, same holds good for a traditional method as well as for a finite element method. There is no difference. Now comes the problem in hand, where you will apply the integrations here, whereas you will convert these in differential equations to a set of algebraic equations. That is where the major crux of the problem lies over here. That means you are doing the integrations and you are solving the problem. But instead, in case of finite element method, we are converting to, first of all, the governing differential equations to weak form. And from the weak form, we are able to get algebraic equations. You don't have, you don't need to do any sort of the integration, and you can just solve the set of algebraic equations. For example, you have x plus y is equal to 2, x minus y is equal to 4. So such kind of a set of algebraic equations you need to solve instead of solving the governing differential equations in this form. Now, in this particular case, what you can get by analytical solution is the temperature as a function of x. That means a single function, whatever the solution function you are getting, which is applicable for the entire region. Please make a note, and it is very important. Whereas when it comes to the finite element, you are getting the temperature distributions at, first of all, at nodes or the degree of freedoms, and then you are interpolating from the nodal degree of freedom or nodal temperatures to within the elements. So that is where the nature of the unknowns changed from continuous function to discrete points or discrete set of the degree of freedoms. So that is where the difference lies from continuum to a discrete set of points, and those points only you are finding the solution. And then you, at any other point other than the node, you can interpolate. Let's say you want to find out what is the temperature distribution in this subdomain or within this element, that will be interpolated from whatever the temperature over here as well as the temperature over here. And then you can approximate either linear, quadratic, what kind of approximation you want. The shape functions you can use and try to figure out what is the distribution among these, what is the distribution among these. So this is where the fundamental difference between the finite element and the traditional method of mathematical analysis, what you do. So where the, very, commonly if you read any textbooks or the literature, they will try to put it in this form, very standard form. K T is equal to F. The K stands for the stiffness, T stands for the unknown temperatures, or here the temperatures, or it may be nodal displacements in case of a structural analysis, and the externally applied force kind of one, which is on the right hand side. But in this equation, these are the algebraic equations. These are not differential equations, and we need to find out what we have is the unknowns T, which is nothing but K inverse into F. So this is where the basic form of the equations which we will solve for any type of the element, whether you look at one-dimensional, two-dimensional, or three-dimensional elements, or any kind of analysis you look at from the field, whether it is structural, thermal, or any other kind of one. This is the basic governing equations that we will solve to get the nodal or discrete locations, the unknown quantities that we will find from this fundamental equation. So those people who are interested in, this reference, I got it from the one of the course, a hands-on introduction to engineering simulation from EDX. This is offered by Cornell University. If anybody is interested, I have given the reference, and it's a code also I have given. You can feel free to take up this. And before I move on, if anybody having any doubt or anything, I'll pause for a minute. You can ask me, or I can continue, and we can discuss following that. Organizers, is it fine if I can continue, or how exactly the sessions usually?
Yes, sir, you can continue.
All right. Let me take water and I'll start. All right, so let's move on. Varieties of these finite elements in varieties of form, maybe based on the shape, based on the theory what you will use, based on the application what you will have. So let's start with based on the shape, or this is not exactly the shape, truly speaking. It is basically the dimensionality. This is the terminology that has been used by the ANSYS software. By the way, I'm not recommending ANSYS software, but I just taken the reference from there, so I just taken its name. And also I come across, in this particular faculty development program, you are already familiarized with ANSYS. I just thought of, making use of the help manual what they provided. It is really good. I really appreciate the kind of ANSYS help manual is available. So let's look at that. So you have the first quantity. There are four types we can think of. Four shapes we can think of. What exactly these shapes? If you look at, one is the point. So this is the point, and you can think of the point or the line or an area or the volume. So there are, depending on the geometric dimensions, you can have these four varieties of the elements. For example, if you like very zeroth dimensions or a point, though I shown a little bit bigger to make sure you can able to see, either it may be defined by the node or as such a mass element. Let's say you are doing the vibration problem and a lump mass you want to analyze, then you can take the mass element, which is just a point. Nothing associated with the volume and other kind of. Inherently, it is possessing some kind of a volume and other kind of thing. It is made up of some density, but as a representation, you can think of as a point or the node. Then you have the line elements. For example, you want to represent a truss or you want to represent a beam, then you can have the collection of the line elements. So that is where, many traditionally, if you look at various varieties of the elements, you can see, especially for beams, you can see in ANSYS, let's say beam 188 is an element type where it is meant for two noded 3D element. So that is where you can have the varieties of the elements you can see in case of the beams and in case of line using the line elements. In a similar way, we can even model the axisymmetric shells also using the line elements, where you can have revolution about one particular axis. There you get a axisymmetry where geometrically and materially, and the loads are it is symmetric, axisymmetric, I mean to say. And then you have the area based, where you have the length and width kind of one, where you can have the quadrilateral element or a triangular elements in order to model the, for example, you want to model a plate, modeling as a plane stress condition, plane strain condition, or axisymmetric condition. You can use these kind of elements. And even, you can use the plate elements as a shell elements further in order to study the behavior of the shells and the plates. So this is where you have 2D kind of one. So I'd like to mention on the right hand side in the figure, where the 0 dimension, 1 dimensional, 2 dimensional, and finally we have 3 dimensional one, where you have set of elements which is a tetrahedral or a brick in shape, and usually used to model 3D solid, where you have geometric input is in terms of X, Y, and Z. So that is where you have the volume elements. There is another variety we can look at from the functional aspects, where it will be modeled. For example, you can think of a bar element, where you, or in a finite element context, some people may also use as a link element. Then you have a beam elements, plate, and solid. So when you look at the functional aspects, I mean to say, for example, if it is subjected to a compression and tension kind of one. For example, in this bridge or a truss kind of one, where you have the members either compression or tension. So that is where we will apply this kind of bar elements or a link elements, and you can able to analyze such kind of a structure. Now, apart from the axial forces, you have the bending forces, where you have the beam kind of a structure. That is where differentiator from bar to beam, where you have, apart from the axial forces, you also, it is subjected to transverse loading, which is resulting in bending action. So that is where you have beam elements. And depending on the cross section, you may have varieties of cross sections. You can think of either open or a closed kind of a cross sections, and depending on your what kind of boundary conditions you have varieties of the beams, you can model it using the beam elements. Whether you model as a complete 3-dimensional body, let's say this is my beam, and you want to model as a using the 3D elements, these 3D solid, I mean to say these, or you can model as a 1-dimensional. Let's say I have modeling as a 1-dimensional, and but the features, the cross-sectional features are taken care at these points. So that is where you can have beam theories or beam model, the beam elements. Then you have the plate or a shell kind of one. For example, you have stiffened panels, where you have skin stiffener, which is of flat in nature, and you want to it is subjected to some kind of a loading or the pressure. And then you need to find out what is the nature, what is the displacements, what is the rotations kind of one. This is where you have a plate model. And there is another kind of one, which is a shell, where the basically, if you have apart from the bending, you have the membrane effect, where it is we generally called it as the shells with the initial curvatures. For example, if you look at a fuselage of an aircraft, that is the central part of an aircraft, where you have the initial curvatures. Maybe here it is 1-dimensional, one direction. It may also have the shells having the curvatures in the other direction also. So this is the radius of curvature what you can get in one direction, the radius of curvature in the other direction. Let's say this is R1, this is R2. So you have the curvature in both directions, and you need to figure out what is the kind of structural behavior by using the plate or a shell element. Now, if your analysis is such a way that you are not able to bring it to any dimensional reduction, where you are unable to bring it to as a truss or a beam or a plate or a shell, then there is no option. Then you have to go with the solid elements. And the solid element is the one which is kind of better element as compared to all this, because there are certain assumptions that to ad hoc kinematic assumptions as involved in all these formulations, whether it is a beam or a plate or a shell kind of one. So solid element, you have the only 3 degrees of freedom. That is the displacement degree of freedoms, and you can model any kind of structure. Even you can model the bar, we can model the beam, you can model plate or a shell, or even the column, which is any kind of one we can model using solid elements. Now, so if you carefully observe where this is in actual practice, let's say this is in 3D, some 3-dimensional, let's say think of as a cylinder, and now I can take the reference surface into the form of 2D and I can model as a shell element. Now, if I take one element out of it and you can look at each node, you can find the degree of freedom. So if I write the hierarchy, one is the element, then nodes, then degree of freedom. So depending on the type of the element, you have the depending on the what number of nodes it is connected and what degree of freedom you are looking forward. Again, it may not be necessarily mechanical, like a displacements and rotations. It may be, let's say, voltage in case of electrical degree of freedom, or magnetism in case of magnetic field you are looking forward. So depending on the field of application, what you are looking, your degree of freedom will depends. So this is one way of looking this kind of approach. There is also, let's say, the case very interestingly, if you look at, let's say I will model the same as a 3-dimensional element, either these, or you can either degenerated form in the form of 2D, or I can model the same as a 3-dimensional one. So you can look at, if I bring out one element, you can see clearly it is a 3D element in shape and it is a 2D element in shape. So that is what you can able to see. And the degree of freedom you need to understand here is the displacements and rotations. Whereas in case of a 3D, it is only displacement degree of freedom. Now the question comes, why there is an additional degree of freedom is coming in rotation? Because we are looking at the mid surface. Then how about the surface which is above or below? That will be dictated, or how the mid surface is rotating, or how your normal is rotating. Based on that, you are able to analyze from the 2D surface itself, you can able to analyze the entire 3-dimensional body. Truly speaking, your 2D element, what you have on the extreme end here, is able to model or analyze a 3-dimensional structure. That is what I want to emphasize, and that is what I want to showcase, that even though it is a surface, a 2D, but eventually in your theory or in your formulation, you are trying to look at how exactly the above and below the material, which is how it is behaving, that will be taken care. So that is where I'd like to introduce the philosophically, let's look at beam theories and plate or a shell theories. So I think many of the people are well familiar with Euler-Bernoulli beam theory, where we are telling the cross section or the plane section remain plane even after bending. What exactly it means is, let's say you have the board, you have the beam, and you have the cross section, which is, this is a cross section or a plane section. And when it is bending, in case of a pure bending only, there is a difference between bending and pure bending where there is no shear force. Let's say if I apply equal movements on both ends, then I can able to get this kind of a pure bending situation where there is no shear force and bending moment is constant. And this is undeformed. This is undeformed, and now you have deformed configuration. And now if you look at the normal or the cross section or the normal, it remains perpendicular to the your mid surface. Let's say if I look at as a neutral axis, then if you look at on the right hand side, I have given this figure. So this is after the deformation, this has happened. And now you look at one important feature is it is straight line, number one. And also it is maintaining exactly 90 degrees with respect to mid surface or neutral layer. That is where you have the Euler-Bernoulli beam theory, and the equivalent of that we can think of as a Kirchhoff theory, where you have the another dimensions you can think of. You have another dimensions like a plate. Okay, here instead of looking at just cross section, in case of a plate or a shell, it is the normal. The normal remains 90 degrees in case of a Kirchhoff theory, whereas in case of a Resner-Mendeleev theory, that is not exactly 90 degrees, it is more or less than 90 degrees. The same thing analogous to the plate theory or shell theory, you have Timoshenko beam theory, where the normal may not be, this is the normal, and this is your deformed profile of the neutral axis, and this is less than or equal to less than or greater than 90 degrees, but not equal to 90 degrees, where the shear deformations are taking place. That is where you have another theory, which is Timoshenko beam theory. So this is where I would like to bring it to your notice. There are two fundamentally different, these are very basic kind of one. There are so many theories with respect to beams, with respect to plates. For example, higher order shear deformation theory, layer wise theory, zigzag theory. There are so many plate theories, shell theories are there, but very focused or very, on a basic level. If you look at, one is without shear, with the shear theories. One is Euler-Bernoulli beam theory, another is Timoshenko beam theory. If you look at, in finite elements also, some of the elements are which is applicable for based on the Euler-Bernoulli beam theory. Some of them are based on the Timoshenko beam theory. So in a analogous to that, it is Kirchhoff and Resner-Mendeleev theory. Now, when it comes to the degree of freedom, as I mentioned, if you look at in case of a beam, we are using just one line. We are representing as a line. Whereas in case of a plate, we are representing as a 2D surface. Now, the degree of freedom at each node, each node varies from 1 to 6 degree of freedom. What do you mean by this? Since some of them already done, a hands-on session with finite element, so they may be already knowing when I am modeling the beam, then you will say if it is within the plane, then you have x displacement u, y displacement v, and a rotation about z axis, which is out of the board, which is theta z. So these are the 3 degrees of freedoms I can think of. Now, if the same one-dimensional element which is available in the space, then you have the x displacement, y displacement, z displacement, and rotations about each direction. So it is 6 degrees of freedom what you can have. In a similar way, even in case of a plate or a shell elements, depending on what you are looking forward, and then you can have only displacement like a W displacement to a rotations and axial displacements also. So that is where you have the displacements and rotations 6 degrees of freedom up to that. But usually, drilling, usually people will call it as 5 degrees of freedom mechanically, and plus 1 rotational degree of freedom, let's say theta z, which is drilling degree of freedom, which may not be considered, or which may be represented theta z as a function of theta x and theta y. So you may generally come across the shell or a plate elements with the 5 degrees of freedom, but in a complete sense, it is 6 degrees of freedom. And also, please remember, I am talking about only the mechanical degree of freedom. But if you are looking for, let's say you are analyzing the piezoelectric material, for example, then you have electrical degree of freedom. Let's say voltage, V, voltage as a degree of freedom. Or you have the temperature. For example, you are doing the thermal analysis, then temperature as an additional degree of freedom you can think of. So the physics of the problem will come into the finite element through the degrees of freedom. The physics of the governing equations will come through theory. Now the shape, what you are looking for, will depends on whether it is a one-dimensional or a two-dimensional kind of elements. Now, I just thought of giving some very basic details about the different forms of these elements, and try to see in the later stage how this can be applied from the point of view of the Gauss quadrature and other kind of thing. Okay, so it's 11:15. So I'd like to, I'm just looking at how speed I am so that I can able to cover the required portion in time. All right, so let's look at this is the element usually designated by the letter E, and you have the nodes, node 1, node 2. That means it is a two-noded one-dimensional element. Now, what kind of a degree of freedom it is having? At node 1 is the displacement U1, and here also another displacement which is represented by U2. So it's a 2 degree of freedom per element and 1 degree of freedom per node. So this is where is very essential in order to get what is the size of your element level stiffness matrix. If you want to find out what is the element stiffness matrix, it is the total degree of freedoms per element. That is what the size of your stiffness matrix. For example, in this particular case, the size of the stiffness matrix turns out to be 2 by 2 because we have 2 degrees of freedom per this element. Now, this is called a linear element. That means you are interpolating linearly. Once you know the unknown quantity at node I, at node J, you can interpolate anywhere in between, and you can have the linear interpolation. That is where you have very basic linear element. Let's say instead of 2 nodes, if I have 3 nodes for this element, let's say this is my first element having 2 nodes only. Now I'll introduce one more element which I am designating with another symbol kind of one to designate whether it is outside nodes and one is intermediate node, and this node will give the more accuracy in terms of the how best you can your displacement quantities or even the geometry, how you can able to interpolate, especially curved boundaries you want to interpolate, or the curved boundary. Let's say your geometry is like this. If I want to use the linear elements, then I get a discretization error of this one. That means you are unable to capture this amount. Whereas if we use the quadratic element, then we can able to bring it more closer and more closer, where it is, let's say if I have only one element with the 2 nodes, and if I use mid-side node, then it will try to have quadratic approximation, which will be more closer, where you can able to interpolate the geometry very well, so that you can have the errors, the discretization errors will minimize this to greater extent. Further, if you want a more refined solution, then you can go for cubic element. But what is the problem in increasing the polynomial order? When you are increasing the number of mid-side nodes like this, that means you are increasing the polynomial approximation. If you have only 2 points, then n is equal to 2. Then the polynomial order which is able to interpolate between these is n minus 1. That is nothing but linear. That means using the 2 nodes, you can interpolate only linear function. Let's say if I have more number of points, okay, let's say n is equal to, in this case is 3, n minus 1 is equal to 2. That means a quadratic representation I can make out between these using these 3 points. That means I am increasing the polynomial order, whereas now if I increase the polynomial order, what is the kind of advantage and what is the disadvantage? As the number of nodes are increasing, your computational cost is increasing. At the same time, advantage, it is you are fitting very closely your displacement field or the geometry where you can able to minimize the errors. Then we look at the another set of the degree of freedom, where you can have the displacement degree of freedom and rotational degree of freedom. Though you have the in actual practice, as I mentioned, beam is a 3-dimensional body, but you are able to represent as a single line like this. Now this line element will have let's say 2 nodes, node 1, node 2, and at these 2 nodes you have the 2 degrees of freedom, that is W1 and W2. One is the displacement in the transverse direction and the rotation which is out of the screen. So this is where you have 2 degrees of freedom per node, what you can have in case of a beam elements. In a same way, even you can think of the elements which are 2-dimensional. That means a 2D beam element, what you can have is where you have the don't worry about the nomenclature, what exactly here it is showing. This is basically taken from SS Rao textbook. It is just to illustrate. I want to show that these are all kind of a representation where you can have the degrees of freedom, whether it is global degree of freedom, local degree of freedom. So whenever you come across any textbooks, don't get feel like I am not aware of this. It is just a matter of how well you represent these quantities. So whenever, let's say this is a beam or some kind of a structure, now I divide it into, let's say, some elements. Now if you look at some quantities which let's say you have 1, 2 and 3 degrees of freedom at each node. Let's say this is 1, 2 and 3. And similarly you have 1, 2 and 3, let's say. So this each individual, if you look at individual, then I am drawing over here. This is a combined, this is at a structure level, whereas individual element, let's say I am taking this E1 and let's say this is E2, usually represented by like this. E1 element is represented by the circle, whereas the nodes are represented without circle, 1, 2 and 3. Now if you look at here, now I will take one element, let's say this is E1, and you have the degree of freedoms, let's say 1, 2 and 3. Similarly 1, 2 and 3. Now there is a quantities I would like to mention here, that one, for example, which we call it as, this is local degree of freedom. DOF stands for degree of freedom. This is global DOF, global degree of freedom. So what exactly it means is, it is a collection. For example, if you look at one element and you have the degree of freedom, let's say 1, 2, 3, then 4. Then you have 4, 5 and 6. So this is the degree of freedom. This is the element, and these are the two nodes what I have. So now these are the local degree of freedom. Now collection of those will give you the assembly process, which will lead to a global degree of freedom. Now, if I want to look at how to designate this local coordinates, for example, in this figure on the left hand side, he used, let's say, small q. Whereas the global degree of freedom, which is represented by capital Q. But it is more or less the same. Only the difference is that it is at local level. And once you put it all together, then it will become a global degree of freedom. That's the only difference point of view. I just want to introduce one more term, which is the global and local. Similarly, if you look at, when you want to model a plate or a shell kind of one, you can think of as a, three-noded triangular elements or four-noded rectangular elements. Now, I have taken from two different sources. That is why the terminology and the figures are a little different. But eventually, it is representing, it's a 2D element like this, and at each node I have 3 degrees of freedom. What are those? One is theta x, theta y, and w. So these are the 3 degrees of freedom at each node will represent how exactly this is bending. Let's say what is the bending about x-axis, what is the bending about y-axis, how much it is displacing in the z direction. So that is the physics of the problem in nature. And now the same kind of one even I can model using the triangular elements. Now it may be 3-noded, it may be with mid-side nodes, without mid-side nodes, with edge nodes, without mid-edge nodes. So you can have varieties of that. I'm going to introduce later, but this is where you can make use of the triangular elements and rectangular elements to model the plate and shell kind of one. And if you look at one variety where people look at as a shell element as a combination of plate element, what we just look at as the 3 degrees of freedom, plus a plane stress assumption where you have the 2 degrees of freedom per node. As a combination of these, you have 5 degrees of freedom, which will able to represent what you call as a shell element. So you can have the 3 displacements, which is represented as U1, U2 and U3, as well as the rotations. Let's say beta 1, beta 2 are the 2 rotations combining together, which will form the 5 degrees of freedom, and that will be able to represent your shell kind of. So you are taking the membrane effect from here and bending behavior from here, and combining together it will forming the shell element. This is one philosophical way of looking, and another is a degenerated shell element where you are equivalent single layer. You are like if you look at in this figure, there is a mid side, mid surface you can think of the same. Now, how do you bring it down? How do you integrate that to get a mid surface? Is the various theories you can follow and get a degenerated shell elements. Many commercial finite element softwares and many literature you can find these kind of elements. Now I would like to talk about the variety of the elements. For example, you have, as I mentioned, earlier we look at only at the corners. Okay, this is a basic element. Sorry, I'm unable to write a very straight edges. But if you look at, we have the 2D element, which is having the 4 nodes at the corner, right? But if you also look at, there is a mid-side node in case of this. Here also you have mid-side nodes. The only difference between this and other varieties is that how do you approximate the field with what polynomial function? If you are looking bilinear function, then you can use this. If you are looking by quadratic shape functions, then you use this one. Or if you are looking for bicubic interpolation, then you can use the third variety what you can have. So third one, which is this one, which is having the mid inside the element, inside the element, as well as on the your edges of the element. So this is where you have the difference. If you doesn't have the mid-side nodes, this doesn't have mid-side nodes, doesn't have inside nodes. Whereas here you have the combination, and also if you look at it is a vector product in both directions. That means if you take a count 1, 2, 3, 4. Again in this direction also 1, 2, 3, 4. It is equally spaced, 4 in one direction, 4 in another direction. Whereas in some cases we can see there is a disparity in that depending on what variety of the element you are choosing. Now, if you look at the one class of the elements, what you can think is serendipity elements. In this kind of one, there is no node inside the element. This is what that means. You don't have the nodes inside. Then such element is called as serendipity. But you can have on the edges, for example, node number 6, node number 5, node number 4 are available on the edges where you can have the serendipity family of this. So this is a lower order element which is called as the 3-noded. If you want higher order, then you can go for 6-noded kind of one. Another important feature with respect to elements is isoparametric elements, superparametric and subparametric. What it means is if you look at the element, any finite element which is meant for the representation of, one is the geometry, like how do you represent the geometry, and another aspect is how it is representing the displacement or rotations. So one quantity is the geometry and another quantity is displacement. If your shape functions, whatever the shape functions you are using the same number of nodes, okay, here if you look at 8 number of nodes, triangles, you count it 1, 2, 3, 4, 5, 6, 7, 8. 8 number of nodes are used to represent the geometry. At the same time, even the displacement also represented by same number of nodes, then you can have isoparametric. Iso means same. Parametric. Here parameter is geometry or the displacement. So same number of nodes if you use to represent geometry as well as displacement, then you can have isoparametric. If it is more number of nodes are using to represent geometry, then you have superparametric. If it is other way around, when you are using more number of nodes to represent displacement, for example, circled one, if you look at here, there is a mid-side nodes also you have, whereas triangles are not there. Triangles are only 4, whereas the display circle nodes are represented are 8. That means you have more number of nodes to represent the displacement field as compared to geometry. Now, is it really necessary to look at such kind of different types of elements? Now, the case of, for example, if it is curved geometry, now I will be more useful if I use superparametric. A curved geometry, I need to be better if I can use superparametric. If they have a geometrically nonlinear situation I want to use, let's say I have a bar, but or a beam, sorry, not a bar, but a beam. Let's say if it is subjected to some loading where the deformations or rotations are large. Now there it will be more appropriate to use subparametric. So this depending on the problem in nature, whether it is the based on the geometry, based on your deformation patterns, you will have different varieties of these elements. traditionally, if you look at any commercial finite element software, they will go with simply isoparametric elements, so that your complexities in terms of the shape functions, then derivatives, finding everything will be very simple. So once you make all these available in the library, you will just call up and they make use of that. So that is the easy way of looking isoparametric elements. But exactly if you are looking at the problem in nature, that depends on the geometry and the displacement field. Now, when it comes to 3D elements, you have a tetrahedron kind of one where you have 1, 2, 3, 4 nodes, or you have the mid-side nodes where you can have higher order elements, or you can have the brick kind of one where it is a traditional element, 8 nodes, or if you have mid-side node, you can have higher order elements, what you can have in terms of 3D elements. Now I would like to bring it to your notice about the local coordinate system and global coordinate system. So if you look at, let's say I have a bar or some kind of a beam, and I'm modeling with a 3D element, and this is where having some kind of let's say length, height, and the width, what you can have, this is what you have, and I'm using 8 nodes to represent this. This is in the global Cartesian coordinate system or a global coordinate system. And yes, ma'am.
સર આપણો ટાઈમ વેસ્ટ થાય છે. આપણે સ્ટુડન્ટને સરખો ન્યાય નથી આપી શકતા. તમે તમારે એમની ક્રેડિટ તો ખરાબ જ.
Ramesh sir, kindly unmute yourself, sir. Okay.
All right. Earlier, I am audible, or just now only it is muted?
Yes, sir, you are audible now.
Oh, fine. So now I am going to talk about the feature of what you call the natural coordinates or the parent coordinate system and the global coordinate system. So why we need such kind of another coordinate system is that, let's say you, for example, some of them may be much familiar with the C++. You have a class, you have an object. Object is a representation or an instance of your class. That means once you define the class, once you know what are the functions defining on how exactly your class should work, then you can have the instance of it where you can have the objects. So that is in a similar way, you define your stiffness matrix in natural coordinate, and then you keep on mapping this one to any other element. So if you look at very simple illustration, let me, trying to look at the option where my pen, I'm trying to look at the pen. Sorry. Okay. Yeah, I'm able to trace out. Okay, so let's look at the case. For example, you have a very simple case, 2D case I am taking. Just think of it as you have a room, and in this room you have 6 tiles, and all are, let's say, same size and same quality, same kind of one, but only thing is they are placed in a different geometric location. Let's say this is my global coordinate, some x, some y, and let's say this is my 0, 0 coordinates, and these tiles are placed in a different geometric location, but the features, it is made up of same material, same kind of fun. So what I will do is I'll take one element out of it or one tile out of it, and I will find out what is the stiffness of this element. Let's say stiffness of that element I will find out, and then I will map from here to here by changing its geometric location. That means I don't need to calculate every time what is the stiffness. Rather, I will create a database for one variety of the element, and then I will keep on calling that. It will reduces your computational effort. You are just calling a function with a stiffness for one variety of element, and then you are giving the input such a way that it will represent different locations what is the stiffness of it. So that is where this is called as natural coordinate system. OK, and whereas this is your global coordinate system. This is also called as parent coordinate system. So natural coordinate system or parent coordinate system is here, and you are mapping to your global coordinate system. Usually the size of this will ranges if it is a one dimensional. If it is one dimensional, please look at here. If it is one dimensional, the size of the element will be -1 to 1. If it is a two dimensional, then the size of the element will be -1 to +1 in both directions. That means you have 2 cross 2. That means size of the 2 units along the length, 2 units along the width. In this case, you have 2 units along the some coordinate direction, let's say xi or s, whatever the kind of, usually the symbols you can see are s, t. This is the one, or Greek letters, let's say, xi, eta, gamma. These kind of letters will be utilized to represent the natural coordinate system, whereas your global coordinate system usually represented by your x, y, z kind of thing. So that is where you can differentiate the dimensionality. One is units -1 to 1, -1 to 1 in both direction. If you have a 3 dimension, what I have given the figure, which ranges from -1 to 1, -1 to 1. Now you may ask, like, you have the size here 2 by 2, 2 cross 2 dimensions, whereas in actual practice it may not be, no. Then how it will be mapping will takes place from here to here. That is where the Jacobian will help you to map one unit area cross section, unit area, to any other area what it is having. The Jacobian will help you to map from natural coordinate to your global coordinate by providing exact what is exactly your sizes. Based on that, it will able to capture. And this is, you can look at, with the different degrees of freedom, what kind of elements you can have. As I mentioned, we can have, 6 degrees, up to 6 degrees of freedom you can have. This is just want to give one or other kind of information one. And finally, I will be looking at 3D elements where each node will have 3 degrees of freedom. That is only displacement u, v, and w. This is the shape of that element, and these are the degree of freedom, and it is having all the 3 dimensionalities x, y, z. Either you can use this one for all variety. All this 3D element can be used as a bar, beam, shell, plate, or anything you can use it. But only thing is you will have only 3 degrees of freedom. That's the only displacement degree of freedom what it is. All right. Now I would like to introduce one more concept, which is called as Gauss Quadrature. Basically, this is the one where we will apply is, for example, you have the stiffness, which usually represented by this form. let's say some dx. The stiffness of the, let's say, line element, or a stiffness of the bar element you want to find out. Let's say this is the stiffness of the element is given by the strain displacement matrix B matrix constitute C matrix, your again B matrix, which is kinematics matrix. Together, if I integrate over the domain, then I can get the stiffness matrix, which is K. But instead of doing this, a definite integration with the limits, whatever the kind of specified, instead of doing that, I will use the numerical quadrature scheme, and one of the popular one among the quadrature schemes is the Gauss quadrature. Based on the rigorous people have worked over the years, starting from trapezoidal rule, Simpson's 1/3 rule, various Newton codes formula, Newton code quadrature, various other quadrature use. But Gauss quadrature is having upper edge in terms of the, when you compare the results with the actual values, the results are much more closer. That is where you have Gauss quadrature. So how exactly this quadrature will work? Let's have a look at. So as I mentioned, you have the stiffness in this form, some limits B transpose CB into dx. Now, instead of working in this definite integration directly, what we will do is we will evaluate the function. This is the function. This is the function. This f, let's say I'm representing as f. Now this function will be evaluated at a certain points. What are those points? Let's say you have the domain 0 to 1. This is the domain 0 to 1. And I want to integrate over this domain. Let's say my function f is going like this. OK, f is going like this, or my stiffness is varying like this. Now I want to find out the same 0 to 1, whatever the B transpose dB. Instead of definite integration, I will go for numerical scheme, where I will evaluate the function, this stiffness B, at certain points. Let's say 1 point, only 1 point, and I will multiply with certain weights. OK, the function evaluated at 1 point, which is designated as S1. The location is S1. Within this domain 0 to 1, I am taking 1 point and multiplying with a certain weight. Let's say that is W1. So if you do this is equal to and finding the definite integration. That is where the scheme Gauss quadrature. So you don't need to do a definite integration from 0 to 1 or -1 to 1 B transpose CB into dx, where you will just take certain points and you will multiply, you will evaluate that function at that point and multiply with weight. You can get that one. So you may consider only 1 point like this. You may also look at, let's say my domain is this and I am evaluating, let's say 2 points. And I know what is the weights, let's say W1 here, W2 here, and I can able to interpolate and I can find out f of S1 into W1 plus f of S2 into W2. So this is where you will evaluate the function or the stiffness matrix very precisely in our finite element context. And you will able to figure out, instead of doing the numerical integration, instead of a definite integration, you will do numerical integration. Now, how many points you will take, whether it is only 1 point, 1 Gauss point, or 2 Gauss point, 3, 4, 5, how many? That depends on your problem in nature. So with a very low order, that is the beauty of Gauss quadrature scheme. With lower order, let's say 1 Gauss point or 2 Gauss points even, is much better results it will give, which will be approximating your stiffness very well. Here I just taken 5 points and the corresponding 5 points location, and I am able to evaluate that integral at those points and I can able to equate it. So I just given the table for your illustration purpose. You can just go through later. I'm sharing these slides with you. So if you have only one Gauss point, so if you look at the table should be read like this. If you have one Gauss point within that domain, the location is at 0. That means exactly at the center. Usually the domain is specified between -1 to 1. So when it is saying 0, location is 0 means at the exactly at the center. And what is the weight you have to multiply? Then you have to multiply with 2. That is the where you have to read this table. Now, if I have two Gauss points, let's say within this domain of -1 to 1, let's say this is -1, this is +1, and you have it minus 0.57735, which is 1 by root 3 minus 1 by root 3. Let's say this is 0 minus 1 by root 3 or 0.57735, and here plus 1 by root 3. These are the two integration points, and corresponding weights are 1 and 1. So this is where you have to read this table as what is the location, what is the corresponding weight, and what is the order in which you can integrate. So it's just to look at this table and try to get familiarized. And the same concept we can extend further for 2D also. For example, in case of 2D elements, it is integral, let's say -1 to 1, -1 to 1, B transpose C B dx dy. That means here you have area integral. That is where you have -1 to 1, -1 to 1, B transpose CB. Now, even this function also, you can evaluate it at those Gauss points. For example, in this, you have, various Gauss points given, 9 Gauss points. So you can have the lower order also, where you can have only one Gauss point or 4 Gauss points or 3 by 3, which we call it as, there you have 9 Gauss points. So depending on the problem in nature, for example, if you are using the shear plate bending, in case of a plate bending problems, I'm just giving an example where you can classify your analysis into 2 parts. One is the bending action and another is shear action. The shear action, you can use 1 by 1 Gauss Quadrature scheme. That means only one Gauss point. Whereas for bending, you can use the 2 by 2 Gauss Quadrature scheme. That means 4 Gauss points you will use. So different order of the quadrature schemes within your program also possible, because you will reduce the computational cost, and also lower order for shear because it will reduces the stiffness. So otherwise it will become more stiffer when you use the higher order quadrature scheme. So depending on the type of the problem you are looking forward, then you will see that what is whether you go for a lower order or higher order. If you want, you have very computational power you have, then you can have higher Gauss Quadrature scheme also. So this is where you have, in terms of the 2D, the points also I mentioned where exactly the location, and you can look at for 3D also. For example, 3-dimensional elements, you need to have integrate -1 to 1, -1 to 1, -1 to 1, let's say B transpose C into B dx dy dz. So you have volumetric integral. That is where you need to have 3D integrals. So this is also again represented or evaluated the function at certain points. You don't need to do all this triple integral. Rather, you will evaluate the function like this and multiply with weights in each direction. And then you will add up, summation will give you the required value. It is just like stiffness of the element. Again, I have given this one. So this is more important. I'd like to everybody to have a patience enough to look at here. I'm sure the time is not very high, but I'll try to see that whatever we covered so far comes together in this kind of a slide, where basically, let's say I want to model a beam element. Now, where is the starting point? The starting point is total potential energy. And everybody knows how to define the total potential energy as strain energy minus potential of the load. Now, the strain energy, which is, let's say in this particular case, I am considering only bending. That is where I have given the expression. The strain energy expression due to bending is m square dx by 2EA. So this is the bending expression. And the potential due to loads. For example, here I have uniformly distributed load and the corresponding load and displacement is V. Load into displacement is the work done or potential due to external loads. That is where I can find this. Apart from that, there is a concentrated forces, concentrated movements. The force multiplied by displacement or movement multiplied by the rotation will give you the potential due to load. So this is where you have the set of all this part from here to here is all about potential due to load. And this part, which is the strain energy part. So strain energy minus potential of the load is total potential energy. Now, you need to, represent as some displacement field. You have the movement, bending moment, that we know that we can represent as a second derivative whole square. Right? M by EI, M by I is equal to sigma by Y, that is equal to E by R. And you can relate the quantities 1 by M is equal to EI by R. I'm trying to connect these two quantities, and I'm able to represent the 1 by R, which is nothing but a curvature, as a function of the displacement V, the vertical displacement V, as second derivative dou square V by dou x square. That is nothing but curvature. First derivative will give the, let's say, V. Theta rotation is equal to dou V by dou x. Second derivative dou square V by dou x square is nothing but your curvature. Okay, let's say kappa. So now R1 by R is a curvature. I can able to represent the above equation in this form, and everything, if you look at everything, is in terms of your displacement field. Okay, one is the displacement field is either the pure translations or rotations also I am able to represent in this form. Now I will able to go to your finite element. Okay, so how do you start again applying from the total potential energy? How do you go to your finite element? The first step again is finding the shape functions. So these are some of the times you already available to you, or you may, if you want to derive yourself, then I have given all the steps right from the beginning. If you have a polynomial order of third order, let's say A0 plus A1 of xi plus A2 of xi square plus A3 of xi cube, you can have this kind of polynomial if you consider. Then you can derive these coefficients A0, A1, A2, A3 by using appropriate boundary conditions, and then you can represent this as a shape functions. Because of the limitation of the time, I am not describing everything, but a final form what it will look like. So this is the what you have initially displacement field V, which is A0 plus A1 into something xi and so on. So can be represented as the nodal displacements as a function of nodal displacement V1 theta 1, V2 theta 2. So that, let's say this is my element, and one is V1, this is V2, this is theta 1, this is theta 2. Okay, so using the four nodal values, 4 nodal degree of freedom values, I am able to represent your displacement field. Now the coefficients of the polynomial which is multiplying with this unknown coefficients v1, v2, v3 up to so on is nothing but your shape functions. That is nothing but, let's say, n1, n2, n3, n4. So that is where I just represented over here. V is the displacement field is represented as a function of shape functions and times your nodal quantities. So this is where you can, next step is, once you have the total potential energy, you represent your displacement field as a function of shape functions. Now you can choose any of the shape functions. What I derived is one set of shape functions only, but you can choose any of the shape function based on what you have in problem in hand. So now you represent your total potential energy phi as a function of your shape functions. Now we will, wherever v is there, wherever v or its derivatives, you represent as a function of shape functions. Now that will be, represented in this form. You need to, a little bit be patient and try to absorb at your end once you go back and try to see each and every step very carefully. I have given all the steps. You can just see that when you take the minimization of this total potential energy phi with respect to displacement fields is leads to that final form I am showing is nothing but your K into stiffness matrix into displacement is equal to your force terms. So this is the final form what you can get once you make the differentiation or minimization of total potential energy with respect to your degree of freedoms will give you to this final form of the equation, which is to be used in the finite element analysis. And then you can form the element stiffness matrix, and then you can, I'm just skipping off all these because of the interest of the time. All right, just 1 minute I will pay attention here. So basically, for one element, let's say this is my total structure. This is in the global coordinate and the local coordinate system. This is one element. This is second element. This is this element. This is this element. OK. Now, for each element, I am able to form this set of equation. K into U is equal to F, or K into D is equal to F. So these are the two element level matrices. Now there is a process called assembly. It's not matrix addition where A plus B, matrix A plus matrix B will give a matrix C. That is not the process here. That is not the case here. Assembly means it's a process where, depending on the location of your degree of freedom, you will assemble the elements such a way that it will give the global level of the stiffness matrix. So that is where the new, one more aspect we need to look at is assembly process. So once you have this assembly process, then what you can get from local coordinate system, what you have here, it will come to a global level of the stiffness matrix. And you take the inverse of this and multiply with the force, you will get unknowns what you have this. Maybe I'll pay attention on this, though it looks very complicated kind of one, but it is not so. If you pay very careful observation, this is the figure where I'm going to talk about one slide only, where I will try to cover the mechanical displacements, electrical, and thermal. So all varieties of the physics related, boundary condition I will cover in one slide. Just pay attention. One is the when it is with respect to mechanical, you have the displacement field. When it comes to electrical, it is the voltage or scalar electrical potential. When it comes to thermal, I'll be using temperature as a degree of freedom. These are all degree of freedoms. Please note, these are all degree of freedom at a node. Now, again, I will go to the next items. One is the stress in case of mechanical, electric displacement in case of electrical, and heat flux in case of thermal. Please look at, I am following in the same order. First one is mechanical, then electrical, then thermal. Then you can have the specified values at the boundaries. So in terms of the traction, you can specify mechanical, electrical charge, or the heat flux, specified heat flux at the boundary. Now, what exactly these and how we will specify? For example, if you look at a three-dimensional body like this, now there is a location where I am fixing here, let's say. Just like in a cantilever, I can fix this boundary condition. Now that boundary I am representing with this symbol gamma of u. That portion is fixed mechanically. Now there is a portion where I will be specifying gamma of pi, where let's say I am specifying the voltage. Let's say 50 voltage or 0 voltage, grounding. For example, grounding I am giving, that means I am specifying the voltage here. And there is this portion where I am specifying the temperature. Let's say I am giving 100 degrees 100 degree temperature at this region. Okay, so this is where I talk about all these boundary conditions, first set, whether it is in mechanical, electrical, or thermal. Then I will specify the stresses, mechanical stress or traction I can specify in mechanical, or electrical displacement I can specify, or heat flux I can specify. And also if it is in case of a cracks or a holes or some inclusions you have, there we can specify as a stress-free boundary condition. For example, I have some center crack or some void I have, and then I can specify on that boundary it is the stress-free boundary conditions. So this is where you have stress-free boundary conditions in terms of the cracks or inclusions where you have. Where you want to specify the loads, where you want to specify the fluxes, you can specify. So this is where in any structural analysis, your boundary conditions plays a critical role, and if you can make analogous quantities of one to another, then it will become very easy. See, for example, here I am specifying what is the traction I have applied. Let's say some forces I am applying in this region. Now in this region I am applying some kind of this force. In this region I am applying some kind of electrical charges. In this region somewhere I am applying some voltage, thermal kind of one. So depending on the problem in nature, you will have the boundary condition in hand. So I'll be skipping all this. So these. So can I take 5 minutes, organizers, please?
Yes, sir.
Yeah. All right. So there are so many online resources available. I just compiled all of them to give some kind of overview about it. So you can find many courses right from India, abroad, and many places. Some of them are government initiatives and some of them are private kind of thing. But you can see all of these resources where you can find out online courses on finite elements and advances in finite elements. And I would like to recommend a couple of the books for your reference. C.S. Krishnamurti, one of the basic book where you can find very easy to understand. And another book is very easy to follow is Jane Reddy. And Zankovich is having a volumes 1, 2, 3. So you can start with one, and if you are looking forward for CFD also, then go to 2 and 3. Otherwise, if you are just a basic finite element, if you are looking, then volume 1 is enough. Otherwise, you can go to up to 3. And those people who are interested in programming, especially finite element method using MATLAB, there is a very good book by author called Young. finite element method using MATLAB by Young and Young Known. The name of the author itself is Young Known. So you can go through that. I find very interesting, and even source code also given there. So you can able to work out your elements, developments, and other research work, whatever you want. So with this, I would like to give some kind of a conclusions from my end. So as you know, there are three methods of any analysis. One is the very you can go for experimental analysis. That is the real what you can get it, but we can not test every specimen and keep on breaking it and finding the strength of it, right? So we need to have some kind of alternatives because it is a very expensive kind of an experimental. So we need to go for some kind of analytical solution, which is a quick kind of one, but at the same time, which is very difficult. Whereas the another intermediate one, which is a numerical method, like a finite difference method, finite element method, the new methods like XFEM and meshless methods, so many other methods are available in numerical schemes. But FEM is having its own kind of identity, whether it is if you look at industry, whether it you look at academic community, it's a very well utilized and very accepted by the all communities. And also whenever you want to make find an optimal product, it is better to go for some kind of numerical studies first, and then you can finally validate with experimental and see how well your product is looking like. And then it is always it will reduces your product life cycle. If you look at the cost will minimize if you go for such numerical technique schemes. But here I would like to bring it some what you have the advantages. At the same time, there is opportunities. Truly speaking, it's not a limitation, rather we can think of as an opportunist as a academic community where we need to see that basically I like to give an illustration with this is the Airbus published report. Basically, they have Airbus A350, which is a very popular aircraft, which is running fine and which is very popular across the Airbus series. But if you look at the cost involved, the time involved, what is being suggested or what is being initial estimate, what is the final cost? It is more like a 3 times, 5 times the cost and the time as involved. Now, one of the important feature where what it could be the reason, if you look at, they mentioned as a lengthy simulations, because if you can reduce the computational time that is involved by incorporating your new method of analysis, new way of schemes, if you can include such a way that your computational cost will reduces, that will reduces your overall time required for the development of a full scale aircraft kind of a one will reduces. That will in turn will reduces the cost. And the another one is material. If you look at aircrafts which is made up of composite material, most of the 50% of them is made up of composite material, and then it is having many layers, 72 layers. We have an interaction with Airbus people, and they mentioned as part of the wing structure, you have 72 layers, and each layer may be some different orientations, angles, and that is where you have different materials and combinations, and you need to take care of all of them. Traditional approaches may not yield required solutions. So accuracy also concerned. The complexity is more. You need to give some kind of a proper constitutive law. That is where we are working for using the variational asymptotic method to give the stress strain relationship or the constitutive law for such a kind of a composite materials or multifunctional composite materials, so that your accuracies will remain, accuracies will be maintained. And we are also looking at reducing the computational cost. Instead of working the 3D elements, we will use 2D elements, that is a dimensionally reduced form, so that your computational cost also reducing, your accuracy also coming closer to your 3D level. So that is where please try to look at some kind of opportunities in terms of the how to reduce the computational cost as well as how to improve the accuracy, so that your end product, not just looking at how beam will bend or how plate will deform, but just think of as a whole structure like an aircraft or a bus or an automobile. Then think of how much cost involved and how well we can able to reduce the cost using the finite element analysis. So there are various advances coming up with in terms of the finite element. I'll just take a minute to illustrate how the XFEM, what we are working is one more domain is applying the extended finite element method. XFEM stands for extended finite element method. So if you look at here, when it comes to let's say there is a crack, let's say a plate is subjected to some kind of a edge crack here. And if you want to model that using a traditional finite element method, then it follows the boundary of the boundary of the crack, and you have to model the entire space using the mesh. Whenever there is a crack propagates, you have to change your mesh, because once earlier it was the crack is up to here. Now it is extended because of your cyclic loading, and then you have to remesh whatever the region it is extended. So you have to entire remeshing need to takes place. That is a time consuming. If you take a small plate like this, it may be okay, but if you look at a real time structures, it is very difficult. So the mathematical rigorous what if you can apply, that is where you help you in by using extended finite element method. You just look at it on the right hand most corner figure, where a regular mesh, you don't need a adaptive or anything, just you take a regular mesh, identify where your crack is there. If you can able to track that crack, then you can able to solve without remeshing. I'm telling, without remeshing, you can able to solve the crack propagation problem. So this is the beauty of extended finite element method. So that is where we are applying to piezoelectric materials as a part of my second PhD student worked on that, and we are extending from 2D to 3D now. And because of the 3D printing is more popular nowadays, which is a kind of a digital manufacturing, where whatever the kind of a structure you think of, it is you have to your imagination. You can create a models, you can 3D print it. For example, if you look at on the top, all are CAD models. All of these are CAD models. In the bottom, all are 3D printed. But how to assess these? How to assess whether which model will give optimal solution? So better is you go for ANSYS or any finite element software, or we also having in-house developed finite element software, and we are able to look at where the stresses, where the displacement, what is the auxetic nature, what we are getting. All this we can able to figure out, and we can get a optimal configuration. So right from the what you design in the more design tool to analysis and then 3D printing, everything you can make out in a digital way. So that is where you can have this kind of analysis will be very useful. I would like to thank my team, the 3 PhD students, and the 4th one is just joined, and this is all about from my side. Thank you very much. But if you have any doubts or clarification, I'll be happy. And
participants, please ask the questions if you have. You are unmuted. Please, you can carry on with the mic only. Please.
One of the question, shall I take up, madam? He is asking which is the best Indian author book to recommend to the students on finite element method, finite difference method, and separately also. So as I mentioned, the book which is C.S. Krishnamurti, which is a very basic book and which you can recommend for students, especially he's an Indian author. He is a professor in IIT Madras. Vast experience, and he given even programs also, even the code also available in that book. You can go through, you can ask your students, there is one way where my recommendation is always better you yourself start coding it. Let it be small element or let it be small contribution, but instead of you can make use the commercial finite elements softwares, there is no doubt, but until unless you code it, until unless you get involved, you may not able to see the real beauty of the finite element analysis. So I strongly recommend to go through this finite element method using Young and Known, which is a very basic book again, though it is not an Indian author, but it is very simple to understand, easy to go ahead, and you can start from there. Or C.S. Krishnamurti, the finite element method book, which I can show you here. It's available. It's the second edition. Now it's available. This is a book what I can have, and people can look forward. And one more question in the chat. Did I answer your question? Is it okay? All right. So there is a one question, if XFEM can go for the natural composite materials also. Yes. See, XFEM is more advantageous of going whenever there is a fracture or a fatigue analysis. Because a traditional finite element analysis can able to take care of composite materials very well, but where the extra coming from or where the drawbacks coming from what your traditional finite element method is overcome based on the extended finite element method. So if you look at, there is a cracks, either edge crack or a center crack, or some kind of various cracks in between in a structure. You want to study what is the mutual interaction among them. So there you can look at the extended finite element method usage very well. Now the material can be even a isotropic material to composite material, again natural or a synthetic or even hybrid kind of one, or functionally graded materials, any kind of material you can. But the advantage is that you can have, when it comes to composite, you have much more complication. In case of let's say look at isotropic material, modeling a crack is little less complex as compared to composite materials. So it is more appropriate to use XFEM there with more rigorous kind of one. Thank you, Bindu Mol, and thanks, Surya Kiran. Sandeep is asking, is there any element available which connects lower order elements to higher order element in the problem? Okay. See, especially when you have the adaptiveness is coming, where you need to make some lower to order. There is always some what you call even if you have mid-side nodes or the inside nodes which may not contribute for the assembly, that will be distributed their stiffness to the edge nodes, or where the nodes are connecting to other elements, and then you can form. In a same way, you can have this kind of let's say you have one variety of the element, another variety of element, where it is having the connection. There you can have the transformation, and then you can have continuity of the stiffness matrices. all right. For XFEM, any reference book. So, you know, there is a Ahmed, Sohail Ahmed, if I remember correctly. That book is very good. First, he will cover up from the fracture mechanics point of view, then finite element analysis, and then they will take it forward to XFEM. So it is a kind of those who are familiar with mode 1, mode 2, mode 3 kind of failures and fracture mechanics terminology. They will find very easy to follow up that book. So if I remember, XFEM by Ahmed. So even the book, which just a minute. This is by Amir, but I know there is a Sohail. Sohail is one which you can think of. Yeah, I can give you exact author name and book title in my presentation. Any advice about implementing wavelet concept with FEM, like wavelet Galerkin method? Truly speaking, I am not an expert in this wavelets, so my answer may be a partial. But if you look at Professor Gopalakrishnan from Aerospace Department of IASC, he is an expert in this wavelets. And also Professor Sandeep Kumar from IIT BHU. He is also well-known person in this wavelets. Maybe even Professor Sandeep Kumar written one book. He shared with me the title and other things. If you want, I can send across to you the details. But it is very easy to figure out. You can just type in Google, you can get it. Professor Sandeep Kumar, Mechanical Engineering, IIT BHU. He had written one book on wavelets. And Professor S. Gopalakrishnan is a professor in Aerospace Department of IASC. You can look at his quite extensively. He worked on these kind of one. You can have a look at on those. MATLAB with FEA book, as I mentioned, Young and Known is very good book. Is additional node in superparametric element take part in solution process, or it will only to capture the geometry? Yeah, see, when we see, even though the geometry as well as the displacement field in some or other way will come into picture in the formation of stiffness matrix, because if you look at integral, it is either integral of dx dy or dx dy dz. So that dx dy dz is represented by, again, some shape functions. So displacement field as well as your geometry, even in what I mean to say is, if not directly, it will indirectly will come into play, both of the fields. So that is the reason, in order to avoid, what you call, what to use and what not, commercial finite element people uses the isoparametric, but it is not necessary. What I mean to say is, as you rightly pointed out, the displacement field, which is truly more predominant in the formation of the stiffness matrix and its effect, but the geometry also plays a role where it is forming in the numerical, let's say, integration of the domain. That integral domain is basically dx dy dz. So there it is been connected. So we can't detach both of them in a unique way. Rather, it is a kind of interdependency of one other. I believe there is a kind of connection on one to other. If you look at especially Jacobian formation, it is dou xi by dou x, dou eta by dou x and all, where your x and y coordinates and the natural coordinates are mapping together. I believe there is a integration of one or a dependency of one onto other. Okay. What is adaptive? That is H P, R, and HP adaptation. Okay, so see, H refinement is very simple, where let's say you have a beam and I am dividing this into, let's say, 10 elements initially. Now I will find out what is the solution of it. Let's say that is not up to the mark, then I will go for further increasing the number of elements. Let's say instead of 10 elements, I will make it 20 elements. That is where you have H refinement. That means element edge length we are decreasing, but the same type of element, whether it is a linear element, quadratic element, whatever the kind of element you are using, same element, but number of elements you are increasing. That is where you are having H refinement. Now comes to the P refinement, the polynomial order. Let's say I have a one element, one dimensional. Now I have a two nodes, that is initially, and I have done the analysis. Let's say I have 10 elements, each element having two nodes only, and then I have done the analysis. Let's say I am not comfortable with that, and I'm looking for, let's say, more, let's say, bending kind of one. Then you try to see that there is a, by introducing one more node, instead of two, I can introduce one more having three nodes. Then it is better to have a more flexible or make it more polynomial order so that you can represent your displacement field. So that is the polynomial order increasing by increasing the number of nodes, usually mid-side nodes. By using those mid-side nodes, you can have the better quality of results. But I am not sure what do you mean by R refinement. Truly speaking, I am sorry, I didn't know about R refinement. And HP adaptation, where you can, increasing the number of elements, increasing the number of nodes, both together you can go for. I think that is HP refinement, if I understood correctly your this thing. And R refinement, sorry, I didn't know what is the R refinement. And best book for Abacus software. So what I suggest is, when you go for Abacus kind of or ANSYS for that matter, doesn't matter whether it is this or that. Truly speaking, I am representing Dassault Center, and we are having Abacus software, as well as the academic version of ANSYS also we are having. And I am, very recently we got into Abacus, but earlier we used to use ANSYS very extensively. These two are quite, very versatile in terms of their, help manuals. Especially if you look at, if possible, I'll share my, screen where you can look at the ANSYS help manual. So it's very informative. You can look at theory manual, user manual. Yeah. So this is, and maybe I'll be if possible, I'll pay attention on one very important aspect is with respect to verification manual, especially in ANSYS. If you look at, there is a good number of verification problems are available. Whenever you are working, you make sure that whatever your learning process, you make sure that you should able to go through all these verification manual. So mechanical APDL, in this there is a verification manual, theory manual, and there is a verification. Yeah, here if you look at, there is a verification manual, mechanical APDL. So it starts from VM. V stands for verification, M stands for manual, verification manual, 1, 2, 3, 4, all these are available. Just clicking randomly, and then you can have so many example problems are available. You can just practice one after another. I think this is the best resource, I believe, rather than you can look at maybe any other book is available, but I believe their reference manuals and YouTube videos, especially for these kind of softwares, these are commercial people, they want to emphasize or they want to commercialize their product to the greater extent. So they're quite extensive YouTube videos are available. You can just type whatever the kind of analysis you want, it is available. And more importantly, I believe this is very good, manual what they prepared in terms of verification manual. And also very good thing is what is the input listing? You can just copy and paste it in the APDL. I'm just talking about mechanical APDL. I'm not very comfortable with the workbench, so I'm just talking about this. I'm an old guy, so I'm looking at APDL. So this is what we can make use of it. And thanks Chauhan ji, thanks Sandeep, and that's all. Okay.
Thank you so much, sir, for your interactive and informative session. And we are very delightful to have you, and you have spared very valuable time with us. Thank you so much, sir. And on
Thanks.
behalf of FDP team and Government Engineering College Bharuch, I thank on their side also. Thank you so much, sir.
Thanks a lot for kind patience of all the participants. All the best.
Thank you, sir.
Thank you.
हेलो।
हाँ पराग भाई.
हाँ आशीष सर, પીપીટી શેર કરી શકું ને?
हाँ करो ना, करो ना.
હા.
માઇકની બાજુમાં એરો કી હશે સર.
હા.
આવો આવો.
A very good afternoon to all of you.
Is it visible on your screen?
Yes, yes પરાગ ભાઈ.
Yes, yes.
Okay, what if I want to do annotations?
It is as per the provision of Microsoft PowerPoint presentation.
Okay, can you see the PPT on your screen?
Not right now.
You are not able to see? Okay.
Yes.
Okay. Presenting give control.
So no need. You have full control. You are presenter right now.
Okay.
Don't give control to anybody else.
Okay. But then why it is not coming to the screen? I have already started sharing, but
We can see that. We can see that screen.
you can see PPT.
Yes.
Okay.
Right now we are saying the Microsoft team from your side.
Okay.
Just minimize this screen, sir.
Okay. Right. Is it fine now?
Yes, sir.
Okay. You can see, na? Fine.
Yes.
Okay. Yeah. Please go ahead.
Yes, madam.
Good afternoon, Parag. Yeah, good afternoon, Parag sir, and good afternoon to all participants attending. Dr. Parag Rajpara is presently working as an assistant professor in the Department of Mechanical Engineering at Marwari University, Rajkot, India. He received his PhD in August 2019 from Sardar Vallabhbhai in National Institute of Technology, Surat, India. He has completed his MTech in turbo machines from Surat in 2011. He has passed his BE in Aeronautical Engineering in Propulsion Division from the Aeronautical Society of India, New Delhi. He has published papers in international journals and national and international conferences of reputed. His research interest includes combustion, heat transfer, and CFD. I, on behalf of Government Engineering College and FDP team, sir, I welcome you and invite you to deliver the session, sir. Please.
Okay, ma'am. Thank you so much for the introduction. And first of all, good afternoon to everyone. I welcome you all in this session, which is on computational fluid dynamics. I hope that I am clearly audible to everyone.
Yes, sir.
Fine. Okay. So welcome you all in this session, which is on computational fluid dynamics, or what we call it as CFD, right? And this session is mainly organized to discuss some of the basic principles, the governing fundamental governing principles which governs the implementation of CFD in practical applications. So we will emphasize on the basic principles, and also we will yeah. Is there any query? Okay.
No, sir. You continue. I think someone's mic is on. You can continue, sir.
Okay, fine. So we will emphasize on the basics of CFD, and we will also look into the applications of CFD by taking an example, right? So basically in this session we will try to learn, we will try to discuss, we will try to understand the fundamental principles that govern the implementation of CFD in practical applications, right? So see, before you start talking about computational fluid dynamics, or what you say CFD, right? The first question that should come in our mind, that what is CFD? Then the second question is why we are doing CFD, or why we need to do the CFD. And the third question is when should we do CFD, right? So we will try to find the answers of these questions one by one as we will proceed into the session, right? So first thing is, what is CFD? So you might have some basic knowledge about what is CFD. You might be using different CFD codes in your research work or in your academics, right? So you might have some basic understanding about what is CFD. So we know that the full form is computational fluid dynamics, but its scope is not limited to the fluid dynamics problems. Although the name is computational fluid dynamics, but its scope is not limited to the fluid dynamical problems. When we say CFD, that means we essentially mean that it's a computational transport phenomena. So it does not involve only fluid dynamical problems. It may be any kind of the problems, it may be any kind of the process which involves transport phenomena. So it may be a heat transfer problem, it may be a mass transfer problem, it may be fluid structure interaction problems, right? Any process which involves the transport phenomena. Then second question is when to do the CFD. So we will try to find the answer of this question also. We will see that what are the important and challenging applications we have these days, right? Where we need to we need to implement the CFD. What are the challenging and interesting applications we have where we need to implement the CFD? Fine. We will also try to find the answer that is CFD inevitable? Are there any other approaches available to solve the fluid dynamical problems or to solve the problems related to the transport phenomena? So that is the third question, that why CFD? What are the alternative approaches? What are the other approaches to solve the transport phenomena? Fine. So here is the outline of the presentation, right? We will talk about, we will start from the basics. We will try to understand what is fluid dynamics, what are the approaches to solve the fluid dynamical problems, right? Then we will come to some of the interesting applications of CFD, right? Then we will discuss about the strategy of CFD in solving the fluid dynamic problems. Basically, CFD is all about it is an approach, we can say, where the continuous problem domain is replaced with a discrete domain. So basically what we do is, in CFD we get approximate solution, we get the solution of any field variable at discrete points. So continuity of the problem domain gets gets sacrificed ultimately, right? But there are benefits also. We will discuss about the positive as well as negative points of all the approaches, right? We will discuss in detail about what is the methodology that we are following in CFD analysis, what is the strategy of CFD. So ultimately what do we do is, the first step and the most important step in CFD analysis is dividing your flow domain into smaller subdomains. So this process we call it as a discretization process. And then whatever the nodes or elements or what we say subdomains or control volumes, it depends upon which kind of discretization method you are using. So we solve the governing equations. It may be partial differential equations or ordinary differential equations, and we convert them into the algebraic equations. Fine. So we will see the different discretization methods, right? We will also talk about the plus and minus points of different discretization methods, which method will be suitable for your problem, for your case. Fine. And how to decide that this method is more appropriate than the other method, right? Then we will explore the different features of a commercial CFD software, ANSYS Fluent. It is a very popular and useful tool, right? Which is used to solve the transport phenomena problems, right? So we will take an example. With a specific example, we will explore this tool and we will see the different options, different features, right? By taking the specific example. And in the last, I will look in. We will look into. We will see that what are the opportunities that CFD offers in different areas. Fine. So now let's understand that first of all, what is fluid dynamics, and then we will try to understand that if you want to solve any fluid dynamical problems, then what are the procedures or what are the approaches that we have available, what are the conventional approaches that we are having, right, to solve any fluid dynamical problems. So see, we all know that fluid dynamics is a subdiscipline of fluid mechanics, which ultimately describes the behavior of fluid when it is in motion. So it describes the flow of a fluid. It has the further disciplines like aerospace, then hydrodynamics. Aerospace is a discipline where we are interested to study the behavior of air when it is in motion. Similarly, hydrodynamics is a we can say sub-branch of fluid dynamics, where we are interested to study the motion of liquid when it is in motion. It has many applications. It has a wide range of applications, which includes not only these are the traditional applications: aerospace, automobile, hydrodynamics. These are the traditional applications. Other applications, or we can say non-traditional applications, not so traditional. So like that, meteorology, oceanography, then of course combustion energy generation, and there are many other applications. These are some of the few applications that we have highlighted here. Fine. Now, the most important thing is the solution to the fluid dynamics problems. Right? The solution of this fluid dynamic problems is mainly based upon the fundamental governing equations. Fine. Now, these equations are a set of mathematical statements which describes the physics of the problem, and your entire fluid dynamics is based on this mathematical statements. So from where do we derive, from where do we get these mathematical statements, from where do we get these governing equations, or which is the factor, which is the factor which governs this fundamental governing equations of fluid dynamics. So these equations are mainly governed by the fundamental principles of conservation. So to understand the principles of conservation, we will try to understand the principle of conservation by taking an example. See, conservation means it may be a conservation of any field variable. It may be a conservation of any fluid property. Let's say if you talk about fluid dynamical problems, it may be a conservation of mass, it may be a conservation of momentum or energy or species or any other variable. But before we talk about the conservation of mass, momentum or energy, right? Let us try to understand the fundamental principle of conservation by taking an example of not mass transfer or momentum transfer or not energy transfer. Let us take an example of money transfer. For example, we will try to understand the fundamental principle of conservation by taking an example of money transfer, and then later on we will apply this concept to the transport of mass or momentum or energy like that, right? So what essentially does the conservation talk about? What is conservation, or what is the principle of conservation? So let's take this example and try to understand the fundamental principle of conservation, right? Suppose you have a bank account. We are taking an example of money transfer. Supposedly you have a bank account. Fine. Now we are talking about the ancient times. We are not talking about the today's time where we have ATM and digital transfer facility and everything. Let's think about the ancient time. Suppose you have a bank account and you want to transfer some money to the bank account, right? So let's say you go to the bank and you transfer some money to your bank account. So you are depositing. So it is in what we can say that is given to the bank account. So you are depositing. So it is ultimately your bank account is enriching, right? So it is in, let's say. So you are depositing, you are transferring some money to your bank account. Now, let's say you think that you want to withdraw some money from your bank account on some day, right? And again, you go to the bank on some day and you withdraw some money from your bank account. So you are taking it out from the bank account. So let's say it is going out of the bank account. So let us say this is out. Fine. So what will be the change in the balance in your account? Will it be in minus out? What will be the change in the balance in your account? Will it be in minus out? No. Why? Because whatever the money that you are holding in your account, right? The bank is paying some interest on that. So some source is there, and this source comes through the interest that the bank is paying to you on the amount that you are holding in your account. So this is the money that comes in the form of interest. So this is the generation of the amount. You can say this is the generation of the amount in your bank account. Then what will be the change in the balance? What will be the net balance in your account? So if you want to calculate that, then what you have to do is the total money that you have transferred to your bank account, that is in, minus the money that you have withdrawn from the bank account, so minus out, plus the money that has been deposited or which has come through the interest paid by the bank. So that is your interest, or you can say generation of the money, right? So this is nothing but it is equal to the change in money or change in balance in your account. So this is ultimately the balancing of what is going in and what is coming out, right? And that is nothing but that is the net change in the money that is remaining in your bank account. So we can say this is a statement of the conservation of balance in your account. Fine. So see, whether you believe it or not, this principle governs the conservation of any physical variable. We are talking about the fluid dynamic problem. So this principle of conservation, right, this statement of conservation of your balance in the bank account, this principle is applicable to any other physical variable. It may be your mass, momentum, heat, mass, whatever it is. Normally, what do we do is this change in the variable, right? We represent in terms of rate. So we can say that the rate of input minus rate of output plus the rate of generation is equal to the rate of change of your balance in your bank account. So if you see this block, right? If you see this block here, this is a specified region through which your field, your property, or you can say your variable is it's transporting. It may be a transport of mass or momentum or energy, whatever. Or your quantity is what we can say it is flowing. So this specified region is known as a control volume, right? So this fundamental principles of conservation, it can be applied to any transport quantity which may be a mass or momentum or energy, and it can be represented in terms of these mathematical statements. Ultimately, these equations or these mathematical statements are they are representing the physics of the problem, and your all fluid dynamics is based on this, right? So now we have understood that what is fluid dynamics and what is the fundamental principle of conservation. Now the question is, if you want to solve any fluid dynamic problem, or let's say transport phenomena problem, right, then what are the approaches available to solve the fluid dynamical problems? See, of course, this session is on CFD, so we should not we should know what is CFD and whether the CFD is inevitable. Is CFD necessary in all the problems, or it is necessary in all the cases? If it is not, then what are the other approaches? See, we should not be biased towards the CFD, because we are having this session on CFD. So we have to find the answer that when we need to apply the CFD, when we need to use CFD, and why we need to use CFD. So we have to understand the other alternative approaches. We have to compare the other approaches that we have, and from that we can find out some conclusion that why CFD is important. If it is important, that where it is applied, in what kind of problems we can solve through CFD. Is it applicable to every flow problem, every fluid dynamics problem, right? So we have to find these answers, and for that we need to understand the different approaches available for us. Fine. So See, by this time we understood that CFD is nothing but it is a numerical simulation of some governing equations for solving the transport phenomena problems. But if you want to solve the transport phenomena problem, then you could have the other approaches like analytical approach and experimental approach. So the question is when we should prefer the other approaches and when we should prefer the CFD. So let's try to look into that, and let us talk about first experimental investigation or experimental approach. See, we should keep in mind that experimental approach is it is very accurate method, and there is no substitute for experimentation, right? Because see, in experiments, whatever experiments tell you the reality, right? So whatever you will see, you will believe it. In case of numerical solutions, what do is we do a sort of idealizations when we are doing the numerical modeling. But in experiments, whatever we see is what the reality is. Of course, there are certain restrictions, there are certain limitations in experimental modeling also. Supposedly, if you want to do the experimental modeling in a full scale, then it is very much expensive, and often it is impossible. Let's say you are designing an aircraft. So before you come up with the final dimensions of the aircraft, right? You have to make a lot of trial experiments with a real size aircraft or prototype. Then it becomes very, very expensive. And in addition to that, see, just like any tool which has some errors, experiments are also having some important errors which are associated with the measurements. So these measurement errors are also one of the issue that is associated with the experimentation. Supposedly, many times full-scale experimentation may not be possible because of several limitations. So one can go with scale modeling. It may be reduced scale, or sometimes it may be you have to use enlarged scale depending upon the problem that you are solving. But again, scale modeling is it is simple, but it is very much difficult to extrapolate the results from the models, because they will not be able to demonstrate what will happen with the prototype. Sometimes it may be because of incomplete similarities. Similarities like, for example, geometrical similarities or kinematic similarities or dynamic similarities. All these similarities may not be properly maintained. And always, whether you are doing full-scale experimentation or you are doing experimentation with means you are going with scale modeling, measurement errors are always the issue associated with the experimental investigation. Fine. So there are some positive points, there are some restrictions, or we cannot say we will not say negative points, but we will say some restrictions, some limitations are there associated with the experimental approach. Right. So this is all about the experimental investigation. Next is theoretical calculations. See, when you are solving the same problem with theoretical approach, then you will have two sorts of approaches. One is analytical approach. The another one is numerical approach. If suppose the problem that you are solving, if the analytical solution exists for that problem, then it is like nothing. Analytical solution is very, very simple. It gives you exact point-to-point solution. But These analytical solutions are possible for very simple flow problems. However, most of the practical cases for most of the practical problems, right? You don't have simple flow problems. You have very complex flow problems, and therefore, for most of the practical cases, the analytical solution does not exist, and it exists only for the few cases. So here comes the role of the third approach, which we know as a philosophy of computational fluid dynamics. CFD can be applied to almost all the practical problems, all the practical fluid dynamical problems. But here you have to remember one thing, that CFD cannot stand alone by itself, right? It needs the help of analytical as well as experimental solutions, because see, you need to validate your results, you need to benchmark your solutions. Suppose if you are solving any complex fluid flow problems, and if you have written some code or if you have developed some code, how will you verify your results? How you will validate your results, or how you will validate your code? So you can validate your code against some problems which are standardized in their solutions, either by analytical means, or there are some benchmark experiments with which you can compare your results and you can validate your code. So we cannot discuss CFD without considering the other approaches like analytical approach and experimental approach or experimental solutions, right? So if you are going with numerical solutions, we can say that the numerical solutions exist for almost all kind of the problems, for every problems. But whenever you gain something, you lose something also. Whenever we say that the numerical solutions, that means we do not get exact solution, we get solution at discrete points and not at all points in the domain, because that is the heart and soul of CFD. That is what we do in CFD. We get solution at discrete points, right? We do not get the solution at all the points in your problem domain. So ultimately, the continuous nature of the solution gets sacrificed. But definitely, the advantage is that you can solve any complex problem and you will get the solution for complex problems. So if you compare the modeling versus experimentation, right, then what are the advantages of modeling? See, the modeling is, of course, it is cheaper. It is not free. Numerical simulations or CFD analysis, it is not completely free, but of course it is cheaper if you are comparing with experimentation, right? Why it is cheaper? Because supposedly you have a code and you are doing some simulations. You can use that code for several different cases, and you can where expenses do not matter. You can use the same code with different parameters, with different conditions, right? So it gives you this freedom. But of course, the computation is not completely free. If suppose you want to solve some complex problems, then you have to use parallel computing, and you need to, it means you will incur a lot of computational time when you need to solve any complex problem. Fine. Then the numerical simulations or the modeling, when you are modeling, you get more clear and complete information. because with experiments you cannot get all the details of all the variables which you are looking for in your problem. But in CFD modeling, it is possible to get all the details, complete information and clear information through the modeling. But in experiments, sometimes it is very difficult, or it may not be possible. Right? For example, let's say if you want to do the measurement of let's say pressure or temperature or any other property, of course you can do that within a complete flow field by simulations, right? But you can also do it by experiment, but that will result into lot of expenses, lot of complexity will increase. Fine. Then the third point is one can handle any degree of complexity as long as it is. Fine. So in simulations, whether you want to believe your simulations or not, that depends upon the level of input that you are giving. Level of input means the material properties, right? Like thermophysical properties when you are solving the fluid flow problems. If you give proper inputs, it will be good. And for proper data, you must have some reliable source. Fine. Apart from that, you have to represent the physics of the problem by applying the proper boundary conditions. If you want accurate results, if you want more realistic solutions, right? You need to take care about this parameters, like you have to take care about the boundary conditions, you have to take care about the property data, you have to take care about the governing equations, models which are appropriate for your problem. So you must have some basic knowledge of means you must have the knowledge of fundamentals of fluid mechanics, heat transfer, thermodynamics, right? And you must have some knowledge about the CFD codes, right? So you have to keep in mind that whenever you are doing CFD modeling, right, you are dealing with the mathematical descriptions. It is all about the mathematical models, mathematical statements, right? So this mathematical description, it may be correspond to the reality, it may not be correspond to the reality, right? So you have to be very precise about this parameters, like for example the material property, then boundary conditions, and the model that is required to solve the problems, right? So we can say these are the advantages, but there are limitations also, because modeling is dealing with mathematical description, so it may not be correspond to what the reality is, and mathematical description can be inadequate. Fine. So we have to consider this means we have to keep this in our mind. Fine. So ultimately, if you sum up what we have understood by this time, that CFD is it is a science of the predicting fluid flow, heat transfer, mass transfer, chemical reactions, and other related phenomena by solving a numerically a set of governing mathematical equations. Right? These governing equations are mathematical statements which are based on the principle of conservation, right? Which ultimately describes the physics of the problem. Then we have also seen that why CFD is important, because most of the real problems are complex in nature. Most of the engineering problems are very complex problems. The governing equations that we are having are coupled and nonlinear partial differential equations, Sometimes the equations become so longer that if you try to solve these equations analytically, then it may be possible that you may miss the physics behind that if you are going with analytical solution. So it is not possible to solve these equations analytically in most of the engineering problems. But it is possible to obtain the approximate solutions of these governing equations, right, through a computer-based modeling, and this is what the subject matter of computational fluid dynamics is. So of course, CFD is we can say that it is an equal partner with pure theory and pure experiments wherever it comes to the analysis and solution of the fluid dynamic problems. What do we do in CFD is that we create a virtual prototype and we do the numerical experiments in order to find out the solutions, right, before we design the actual prototype, right. It is CFD helps to test the virtual prototype, and you can analyze the different situations. You can change number of variables, you can study the results, right, and you can find out your optimum design. Fine. So this is what the importance of CFD is. Now, when it comes to the benefits of CFD, so far from our discussion, we understood that whenever you want to solve the complex problems related to the fluid dynamics, right, without CFD, it is quite impossible, we can say. CFD complements both experimental and theoretical fluid dynamics, right? So it is we can say it provides alternative cost effective means of simulating your real flows. How the CFD helps you to solve the complex problem? If you talk about the insight of CFD, then it provides you better visualization and enhanced understanding of the fluid flow that help you to find the optimum configuration for your system or optimum design for your system that you are going to develop. What is the foresight? See, testing many variations until you arrive at optimum result before physical prototyping and testing. So ultimately, you can test any system, any virtual prototype, and you can do the variation in terms of parameters, conditions, whatever kind of variations, whatever situations you have, any number of situations, any number of variations you can do until you arrive at your optimum solution. So that reduces your overall costing, that your expenses, right, that you need to do for if you directly go with experimentation. So experimental trials will be reduced. Practically, CFD helps you to find out your optimum design without any added expenses. You can do unlimited level of simulations, and you can get unlimited level of details of your results at virtually no added expenses. Fine. So these are, we can say that some of the important points which highlights the benefits of CFD. Now, right, so it has been highlighted here also. There are a few points which ultimately speaks about why CFD and what are the major benefits of CFD. So ultimately, the simulation results in prediction of the flow fields and engineering parameters, they are very useful in design and optimization of any process or any equipments or any system, right? There will be substantial reduction of the lead times and cost of new design. Fine. Then you will have the ability to study the systems where the control experiments are very difficult or sometimes it may be impossible to perform in case of very large systems, just like we have taken an example of aircraft. We can have the ability to study systems under hazardous conditions at and beyond their normal performance limit. So you can have safety studies and accident scenarios. So suppose you talk about application of CFD in automobiles. You are interested to study the flow over a outer body. You are interested to study about the interior, like for example, if you want to design the air conditioning and ventilation systems for better comfort of the passengers, right? So this kind of real problems can be addressed, and CFD has a potential to play an important role in this kind of real problems. Fine. So yes, through these pictures, right, it highlights these 4 points, or we can say the 4 major benefits. First of all, it reduces the system cost. It helps to understand the problems, helps to analyze the problems, helps to find out the optimum design. It also helps to improve the performance of your system. Fine. And we can say that it reduces the design time and the overall cost that you need for experimentation or to develop your product or system, whatever it is. Now, we are going to look into some of the applications of CFD, some of the interesting applications, right, of CFD in next few slides. So let us see the first application, that is the application of CFD in aerospace. It is, we can say, one of the most common and traditional application, right? So let us consider this. Let us say you have an aircraft. When you say aircraft, then aircraft has interior and exterior both. If you consider the interior, then it includes the design of your air conditioning and ventilation systems like that. When you have an exterior, then you basically consider flow over an airfoil section, which you are intending to model, for example, right? So supposedly the other components, like for example, you have a combustion chamber, right? So you want to know the transport phenomena within the combustion chamber, how the reactions are taking place, what is the performance, right? What are the emissions and what is the efficiency and all these things. So we want to understand the reaction chemistry, we want to understand the transport phenomena. So one can have CFD for this kind of applications. One can have CFD for a spacecraft application also, right? Then the another traditional approach is automotive application of CFD in automobile. So again, here the basic philosophy is same. You want to see the fluid flow behavior inside the car. The whole idea is to design the car so that passenger feel comfortable. Other important consideration, like how the fluid flow takes place in the outer body, right? And what will be the resistance, drag resistance across the car, means how the flow takes place outside across the car body, and how to determine the drag force on the car. Also, you have a combustion chamber design is also very, very important, right? So CFD has potential to do this kind of analysis in automobile applications also. So when we say automobile or aerospace applications, these are very traditional applications of CFD. But when there are many applications which are not so traditional, right? And but they are important, and they are used in modern days where we are using CFD. So one of the application is biomedical, right? So you can see that this is a human heart, which is modeled as a pump in CFD, right? Then you can see this also, the flow through arteries, where this is very interesting case where the fluid flow analysis is very, very important. right? So next, CFD is it has a lot of applications in chemical industries also, right? Whenever there is a mixing of two fluid streams, or whenever there is a separation or injection of the fluid streams, right? This type of complex problems we can capture by CFD. CFD has a very big role in solving this kind of problems, right? Now, see, chemical application is a sort of traditional application, right? But you have applications of CFD in designing the electronic devices also, right? So this we know that with the advent of electronic devices, the sizes of the electronic devices are getting more and more reduced nowadays, right? So supposedly you have some you have same power rating. Then what you want to do? You have to dissipate more and more amount of heat